Huntington Ingalls Industries, HII, confirmed that its Newport News Shipbuilding yard has successfully wrapped up builders' sea trials for USS John F. Kennedy, CVN-79, the second nuclear-powered aircraft carrier of the Gerald R. Ford class. Following its initial period of operations at sea, focused on exercising and verifying key ship systems and major components, the carrier has returned to Newport News. The trials involve close coordination between shipyard specialists, the ship's crew, and U.S. Navy representatives, all working together to assess the vessel's overall performance and operational readiness. Derek Murphy, Newport News Shipbuilding Vice President of New Construction Aircraft Carrier Programs, said, "Taking Kennedy to sea is a testament to the grit and determination of the world's finest shipbuilders. The Ford class represents a major generational advance in U.S. Navy aircraft carrier design, incorporating new technologies and operational improvements over earlier supercarriers. USS John F. Kennedy is slated to take over from USS Nimitz, which is expected to retire around 2027, although an extension remains possible to preserve a 12-carrier fleet. In the decades ahead, ships of the Ford class are intended to phase out the Nimitz class on a direct replacement basis, maintaining fleet size while delivering greater efficiency, power generation, and future growth potential." In this video, Defense Updates analyzes how USS John F. Kennedy improves on Nimitz-class supercarriers. Before we proceed, a word on NordVPN, which is one of the most trusted and fastest VPN brand that has a no-log policy validated by Deloitte. NordVPN provides a 256-bit encrypted tunnel that protects your privacy and also enables you to access contents that are blocked based on geolocation. Its threat protection system helps you avoid phishing, scams, and malware. NordVPN application is available for all the major platforms as well as browsers. Get an exclusive NordVPN deal with massive saving by going to nordvpn.com/defense or clicking the link in the description. It's risk-free with Nord's 30-day money-back guarantee. Maintaining stability is fundamental to any naval vessel, but it is especially critical for aircraft carriers, where safe and reliable flight operations depend on a steady deck in all sea states. The U.S. Navy's 10 Nimitz-class carriers have undergone successive upgrades to address evolving threats. However, a 2005 RAND study warned that years of modernization had significantly increased overall displacement and raised the ship's center of gravity, degrading stability to a point where adding more topside weight was no longer feasible. Ford-class carrier USS Kennedy is designed to correct this structural imbalance from the outset, providing greater growth margins so that future capability enhancements can be integrated without compromising stability at sea. The Ford-class carrier incorporates a high degree of automation, a design choice that has driven up upfront procurement costs. However, this same approach is expected to significantly lower long-term operating expenses. USS Kennedy will sail with a crew of roughly 2,600 sailors, around 700 fewer than required for a Nimitz-class carrier. Over a projected 50-year service life, a Ford-class ship is estimated to cost about $4 billion less to operate than its Nimitz-class predecessor. Reduced manpower and greater automation also decrease reliance on human-intensive processes, lowering the risk of mistakes. This is particularly relevant given the U.S. Navy's recent experiences with operational setbacks linked to human error. Nimitz-class carriers rely on steam-powered catapults to launch aircraft, a technology that depends on extensive steam plumbing, large condensate recovery systems, and significant quantities of fresh water. These complex mechanical arrangements are maintenance-intensive and add to the overall workload of the ship's crew. Another limitation of steam catapults is how launch force is applied. Most of the energy is delivered in an abrupt initial surge, creating a sharp jolt that places considerable stress on aircraft structures. Over time, this repeated strain can shorten the service life of extremely costly airframes. By contrast, the Ford class introduces the Electromagnetic Aircraft Launch System, EMALS, making it the first carrier designed to abandon steam catapults entirely. While installation of EMAL in USS Ford faced several challenges, but those issues seem to have been rectified, and installation in USS Kennedy was much smoother. EMAL employs a linear induction motor, using controlled electrical currents to generate a moving magnetic field that accelerates a launch shuttle along the deck. Because power is applied smoothly and progressively, the system avoids the harsh loading associated with steam launches. This more refined launch profile not only reduces wear on aircraft, but also makes email better suited for future combat aircraft and unmanned platforms, such as the Boeing MQ-25 Stingray. When recovering aboard a carrier, an aircraft must be brought to a stop over a very short distance, making assisted landing systems essential given the limited deck space compared to a conventional runway. On Nimitz-class carriers, this role is performed by a hydraulically based arresting system. While effective, it brings aircraft to a halt abruptly, subjecting the airframe to sharp deceleration loads. Repeated exposure to these stresses can accelerate wear and reduce service life, a concern that is even more pronounced for lighter platforms such as unmanned aerial vehicles. USS Kennedy, however, is equipped with a far more advanced electromagnetic arresting gear. This system precisely controls braking forces, allowing aircraft to decelerate in a more gradual and controlled manner, resulting in a smoother recovery and reduced structural strain. Working in tandem with emails, the Advanced Arresting Gear, AAG, is expected to significantly boost operational tempo. The Ford class is projected to generate about 33% more sorties than its predecessor, approximately 160 sorties per day in routine operations, rising to as many as 270 sorties per day during high-intensity combat. At the core of every aircraft carrier are its nuclear power plants, which generate the energy needed to operate the ship and its systems. The Ford class introduces an entirely new reactor design to meet far greater electrical demands. Each ship, including USS Kennedy, is powered by two Bechtel A1B PWR nuclear reactors. Individually, these reactors can generate roughly 300 megawatts of electricity, 3 times the output of the reactors used on Nimitz-class carriers, which produce about 100 megawatts each. This dramatic increase in available power provides substantial headroom for future capabilities, including energy-intensive systems such as directed energy weapons and other advanced technologies. In addition to higher output, the A1B reactors are significantly simpler in mechanical terms. Compared with the Nimitz-class reactors, they incorporate far fewer valves, pipes, pumps, condensers, and generators. This streamlined design reduces maintenance requirements, lowers lifecycle costs, and frees up valuable internal space within the ship. To control costs and improve commonality across the fleet, the U.S. Navy selected the Enterprise Air Surveillance Radar, EASR, as the standard radar for future aircraft carriers and amphibious ships, even though the lead Ford-class carrier was originally equipped with the more complex dual-band radar. While simpler than dual-band radar, EASR still incorporates several advanced features, including fire control quality tracking. Adapting EASR for USS Kennedy is expected to save the Navy several $100 million. The system is designed to consolidate and replace the functions of legacy shipboard radars, such as the ANSPS-49 and the three-dimensional ANSPS-48 air search radars currently used across much of the surface fleet. While there is no publicly released figure that defines how much more powerful EASR is, as compared to legacy radars such as the ANSPS-49 or ANSPS-48, the improvement is thought to be significant. Unlike the mechanically scanned analog-era SPS-49 and the partially electronic SPS-48, EASR is a fully digital AESA radar derived from the ANSPY6 family and built with gallium nitride transmit/receive modules. This allows far greater sensitivity, faster update rates, and much higher track capacity, particularly against small, fast, and low observable targets such as sea-skimming cruise missiles and UAVs. Navy briefings have indicated that SPY-6-based radars can offer up to roughly 30 times greater sensitivity than legacy systems in certain modes, not through raw transmit power alone, but through superior signal processing, beam control, and electronic protection. In practical terms, EASR can detect threats earlier, track many more targets simultaneously, and operate effectively in heavy clutter and jamming, enabling a single radar to replace multiple older systems while delivering a clear generational leap in capability. The Advanced Weapons Elevator (AWE) system on the USS Kennedy marks a significant technological advancement over the legacy weapons handling systems used on the Nimitz class. Designed to streamline the transport of munitions from deep within the ship to the flight deck, AWE plays a critical role in improving operational efficiency, safety, and sortie generation capacity. On Nimitz-class carriers, weapons elevators rely on traditional cable-driven hydraulic systems. These elevators are labor-intensive and require more sailors to operate. Their design also involves numerous manual steps to move ordnance from the magazine to aircraft loading areas, which slows down the rearming process. The older system is functional but relatively slow, with bottlenecks in both handling speed and availability, particularly during high-tempo operations. In contrast, the Ford class introduces 11 advanced weapons elevators, powered by electromagnetic motors and guided by linear induction systems. These elevators operate without cables or hydraulics, reducing mechanical complexity and increasing reliability. AWE can move up to 24,000 pounds of ordnance at speeds of up to 150 feet per minute, and they travel vertically across up to 7 decks. Crucially, the elevators open directly onto the flight deck and hangar deck without intermediate staging areas, allowing for faster, safer, and more direct movement of munitions. Although the Nimitz-class supercarriers are known for their robust construction, the Ford class raises survivability standards even further. This was demonstrated during the full ship shock trials, FSST, conducted on USS Gerald R. Ford. On June 18, 2021, the carrier underwent its first planned shock test, during which the U.S. Navy detonated an explosive charge weighing roughly 20 tons, 40,000 pounds, in close proximity to the ship. The resulting shock was powerful enough to register about 3.9 on the Richter scale, an effect comparable to the simultaneous detonation of around 100 modern depth charges. Such extreme testing is designed to replicate the kinds of underwater blasts a carrier might experience in combat, whether from anti-ship missiles, naval mines, torpedoes, or secondary explosions caused by nearby vessels being struck. FSSTs are comprehensive by design, examining not just hull strength, but also the resilience of onboard systems, including electronics and components associated with the nuclear propulsion plant. Over a 4-month period, USS Gerald R. Ford was subjected to 3 separate underwater explosions, each conducted at progressively shorter distances. The carrier completed its third and final shock trial on August 8, 2021, with outstanding results. According to its commanding officer, Captain Paul Lanzalota, the ship suffered no catastrophic failures, flooding, or fires during the entire test sequence. USS John F. Kennedy, built to the same Ford-class standards, incorporates the same enhanced structural strength and system resilience, ensuring comparable levels of survivability in high-threat environments.